Probability, new unit. This is just a quick little overview. I've handwritten here favorable outcomes over possible outcomes. It's important enough that it's worthy of your notes. Everybody grab your notes section. We don't write too many things in here, so that must say something to you. Probability starts out easy and ends up hard. These are going to be a challenge. Today's going to be easy, but by the time we get done with it, we're doing stuff that the vast majority of adults off the street could not figure out. Probability always comes down to this simple statement, that it's the favorable outcomes over or divided by the possible outcomes. So if this was as simple as a coin, what are the possible outcomes when you flip a coin? Heads or tails? Heads or tails are the outcomes. And there's two of them, so you'd have a 2 on the bottom. And then if you pick one, like you pick heads, then you have one favorable outcome. All right. Now, of course, it gets a little harder from here. I'm going to take some data from my last class, and just we don't have to take the time right now to create it. We'll just use their data as far as people who are male or female and have a dog or not have a dog. So this right here, for example, is 2, means that they were a male who did not have a dog in their family. All right. Are you curious about your class? That's all right. I can tell some of you are a little curious about that. We'll just do it really quick. In here, who are my male people who have a dog? Raise your hand, please. We'll create the data for our class. 1, 2, 3, 4, 5, 6, 7, 8. And my male people who do not have a dog at their house. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I'm ready to do a total. 8 and 9 is 17. All right, I'll rewrite that in red just because it's bothering me. I'm going to change to green and go with my female people who have a dog. Raise your hand. 1, 2, 3, 4 of you. And my female people who do not have a dog. 1, 2, 3, 4, 5, 6, 7, 8. And now I can get my total there is 12. And now I can get all my totals. Across the top, I can go 8 and 4 makes 12. 9 and 8 makes 17. And 17 and 12 makes 29. So there's obviously 29 of you in here right now. Okay, this is called a contingency table. And you can do probabilities based on these. This is meant to be just a quick lesson on this because this stuff goes pretty easy. Now, most of the time when you've done probabilities in the past, you always just take the grand total number of kids and that's always on the bottom because that's always the possible. Like if I'm going to pick one of you guys, okay, and there's 29 of you in here. So then there's a 1 in 29 chance that I would pick you. Well, if we use a contingency table, there are a lot of different possibilities of how we can divide this up. Let's say I was going to toss the magic ring, you know, the one ring to rule them all. Know what that comes from? Lord of the Rings, yes. And there it is. And I'm going to toss it over my shoulder, and I'm going to see where it ends up going.
Oh, yes.
All right. Van, I think you stole it, but that's all right. You got the one ring. So now, what was the probability that I was going to toss it to a male person? You can do it from the chart right now. Everybody figure it out. You can't just say 17. That's not a probability. 17 out of 29. Okay. So everybody was possible that I could have thrown it to, right? Now, obviously, there's probably some, things that were not fair about it because obviously somebody that's kind of in the middle is more likely to get it from how you're just going to throw it, but it's possible it could have gone to anybody. Now, what if I change the probability? Can I have that back, please? Thank you. What if I change the probability to, I'm going to only throw this, I'm going to throw it out there, but whatever boy it gets closest to is the one who is it. The one person got picked. Does that change my probability? Because remember, it's a favorable over possible. And what part did I just change? The possible, the one on the bottom. So it is not a 29 anymore. What's it out of now? If only the boys matter, it's going to be out of 17. And then, what's the probability that I will get it to a dog lover? Dog owner, at least. 8 out of 17. Notice it changed to out of 17. That was the main thing. And that's something called a given. This is important enough to put in your notes. A given will change the denominator. These are the hard kind. As soon as you get to something that says, given that it goes to a boy, the whole problem just changed. Now it has to be out of the total number of boys instead of the total number of people. The next one that's important to understand is ors and ands. All right, let's say that I am going to be happy, or my favorable outcome is if it goes to a dog lover that's either a male or a female. I don't care. Either one is okay. So I win if it's a dog lover male or a dog lover female. Then does my probability increase based on that compared to just a dog lover male, for instance? So when I say dog lover male or dog lover female will make me win, then I've changed my top of my fraction. Because I still could go to anybody, which would be out of 29, but it could be male dog lovers or the female dog lovers. And the male dog lovers is how many? 8. And the female dog lovers is how many? 4. And so now it's 8 and the 4. And what do you think I should do with the ors then? Add them. Add them is correct. So it would be 12 out of 29. And you could have found that right here too. So ors make your probability increase. I'll give you another example. Let's say I was just going to throw this ring out to somebody in class and I win if it gets to a blonde person. And then I change it and say, you know what? I want more chance of winning. I want it to be a blonde person or a person who owns a cat. Does that make me more likely to win? Yes. So ors increase your probabilities. So if I increase the probability, am I increasing the top or the bottom? The top. So your ors make you add the things on the top. And how about this? You just assume then that the other one must be subtract, but it's not exactly that simple. If I say and, let's see what happens to probability. I say I want to throw this out and I want to give it, I hope to get it to a blonde person. Okay, that's going to be some number out of 29. If I say it has to be a blonde person and they have to have a cat, does that make my probability lower or higher? Lower. Because there's less people, right? That you have to be blonde and have a cat. Raise your hand if you're blonde and have a cat. All right, so there's 2 people that would win in this class. All right, 2 people that are favorable outcomes out of 29. All right, so the point is, if you see the ands and the ors, you need to know what to do. And the ands are not something that makes your probability increase. And sounds like it's like plus, but it doesn't work that way. It's one of those counterintuitive kind of things. All right, so let's go back to our chart and let's ask one more question here. Would you please figure out for me, given that I'm going to toss the coin to a girl, what's the probability that they will not have a dog? They will be a not dog person. Given that I'm going to toss it out there and the girls are the only ones that can win. So as soon as I said given, Van, what did I change? Denominator. So it wasn't out of 29 anymore. It's out of what? It was given it was a girl. 12 possible. And what were the favorable ones? The 8, the not dog people. So it was 8 out of 12. And for the purposes of our probabilities for this entire chapter, divide them and round them to 3 decimal places. So 8/12 would simplify to 4/6. Somebody divide that quick. Actually, you probably could do it. 4/6 simplifies to what? 2/3. What decimal would that be? 0.6 repeating. So what I would ask you to do is in this case, the evil number, 0.666. And except the last number rounds up, right? It's going to end up being 0.667. You need to go out 3 decimal places and round the last decimal place either up or down. All right, so your answers are always going to be 3 decimals. Don't ever say 1/2.